Welcome back to the details video about the MEMSIC high performance 3-axis magnetic sensor, which we will use to make a digital compass. I already did a basic video about that chip in which we had a quick squiz at the datasheet and used an existing library to get the thing up and running with an Arduino, and where we, or at least I, was very impressed about that thing's performance out of the box with a box standard library. And without any calibration. Card here, link in the description. In this first detailed video, we will have a deeper look into the datasheet and we will start to write our own I2C library for that thing and the Arduino. Enjoy! Before we have a look at the register map given here in the datasheet, I want to talk a little bit about that 16 bits, 18 bits operation modes that is sometimes mentioned here in the datasheet. We already saw in the basics video that the thing can do 18 bits operation. Now the word mode is a little bit misleading because the MEMSIC MMC5983MA always does 18 bits measurements and always delivers you 18 bits of data. But you are free to read only 16 bits of data out. Yeah, that's it. So there are not really two different operation modes for 16-bit and 18-bit operations. Keep that in mind, please. Here's the register map. So the registers are all addressed consecutively starting from 00 to 0C. There's an outlier here. We talk about that later. The first 7 registers contain the magnetic field data. So you have X out 0 and XY 0 and then Y0, Y1 and Z0 and Z1. And these pairs of 2 bytes, so 16 bits in total each for X, Y and Z, contain a 16-bit value for the magnetic data. To be more correct, the 16 most significant bits of the magnetic data, so bits 17 to bits 2. And then you have this additional register here, which only contains 3 times 2 bits, and that's the additional 2 least significant bits for the X, Y and Z magnetic data channel, bringing each channel up to a full 18 bits resolution. So the 16-bit mode really only consists of you not reading that 7th register here. Here are the register details for the X channel. So we have at the address 00 hexadecimal the X out 0 byte, which contains the most significant bits 17 to 10. And then next at 01 hexadecimal we have the X out 1 register, which contains the next 8 bits, and then we have this shared register here, the 7th register at address 06 hexadecimal, the XYZ out 2, which contains the 2 least significant bits for the X channel and also for the Y and the Z channel. It's the same for all 3 channels. And here you see the 16 bits operation. You just read the 16 most significant bits, and for 18 bits operation you just read all 18 bits. That's it. And it's exactly the same for the Y and the Z channel, so we won't have to have a look at those. Then we have a lone 8-bit register for the temperature output of the built-in temperature sensor. The temperature out register T out at hexadecimal address 07 is a meager 8-bit value, and it can represent temperature values between -75 and +125 degrees Celsius with a meager resolution of 0.8 Celsius per least significant bit. Yeah, and 0 is -75 degrees. After the temperature register, we have the status register at 08 hexadecimal and then 4 bytes of control registers 0 to 3 from 09 hexadecimal to 0C hexadecimal. Unfortunately, the information given in the datasheet for these 5 registers is very sparse, not even 3 pages and not very well structured. So I made my own register cheat sheet for the chip, and we will have a look at that later on. Finally, we have the product ID 1 register at hexadecimal 2F. That's a little bit of an outlier because, as you can see, there's a large gap between the last internal control register at 0C and the product ID 1 register. The product ID 1 register contains the fixed value 00110000 and is of course just read-only. If we turn a page in the datasheet and have a look at the I2C data transfer section, we'll read that the I2C slave address of the device is 01100000, so exactly the content of that product ID register 1. While you can read that, I don't know, maybe they just included it because they can. And here's the cheat sheet I was talking about that I made up. So we have here the status register and the 4 control registers, and the bits are color coded. So gray is obviously reserved. Green means that's a read-only bit. We have only one of that here. Yellow means it's a read-write bit. And orange means you can write a 1 to those bits to cause the chip to perform a certain action, and afterwards the chip will reset these bits automatically back to 0. I will make that cheat sheet available as PDF download, link in the description. Anyway, please note that the status register contains only 1 read-only bit and 2 read-write bits, so you can actually control something with the status register. So the status register is really just another control register, okay? I won't go over all these configuration options and control options here in one go. Instead, we will talk about the different config bits here as we already implementing the code in the library for them. And some of that stuff is so badly documented that it will need some experimentation, and we will have probably to get out the oscilloscope too. But anyway, in this video I want to be at least able to take a single magnetic field measurement with that thing and read that measurement out, of course. And to do that we only need one single bit, and that's TM_M. That is take magnetic measurement. Please note you can either take a magnetic measurement or you can take a temperature measurement. So if you set a TMM for the magnetic measurement to 1, then TMT, the bit to take the temperature measurement, must be 0. You can't do both at the same time. Anyway, let's get started with the code. I will this time take a top-down approach in explaining the code I've written so far. So we start with a sketch. Of course, we need to include our wire library from the Arduino environment. We need to include our MMC5983MA _ I2C library. We will have a look at that at .h file in a second. And then we have to initialize a MMC5983MA _ I2C object here, and we're passing a pointer, a reference to the wire object. The setup is primitive. We just initialize our serial interface here so we can see something in the serial monitor, and in the serial plotter. Then we do a wire begin and a wire set clock to 400 kilohertz. That's the maximum clock frequency for the I2C bus the chip supports, according to the data sheet. Then we come to the loop. In the loop, we first execute here a library method to read the access output from the chip into our library object. Then I use serial print to print out the 3 values in 18-bit of our access. Here, these methods use a numeric argument as the access XYZ012, and then I command the chip to take another magnetic measurement. That is, I'm setting that take measurement magnetic TM_M bit again. And then I wait for 100 milliseconds because, yeah, this takes a while, and the loop starts again. So actually how I structured the loop here, the first measurement is maybe empty, 0 or invalid, but I don't really care. In the .h file of the library, we first have the usual, if not def, define stuff, which is of course closed off at the end by an end if. So we won't include all that stuff here in the .h files multiple times. And we include our standard Arduino library, and of course we need the wire library, and then here is our class with the public part, which starts first with a enum definition for errors here. And since I'm doing I2C, I have here errors defined for several I2C errors that can occur. That's just housekeeping, and that's nothing new. I did the same in almost all libraries I did to this point. Then we have here a constructor that gets, we saw that in the sketch itself, a reference to a 2-wire object as argument, and the default constructor is actually deleted. Yeah, I omitted that in other libraries I wrote so far. Anyway, we have also a destructor, which basically does nothing, so we don't need to talk about it. Then we have the basic commands here, and these are commands that are causing the chip to perform a certain action by writing 1 to one of the register's write-only bits. And I've implemented only the first now, and that's the take magnetic measurement. Yeah, it causes the MMC5983 to take a single magnetic measurement. Please note, these measurements can, depending on other settings, take between 0.5 milliseconds and 8 milliseconds. And the usual return true if successful, otherwise false. And then we have a last error method to retrieve the fault condition. And that last error method will, of course, return something of the type here, error. That's it for commands. Then we have read commands. These are just reading data from the MMC5983 registers into the objects registers array. So I have a byte array registers within my class here, and that shadows the content of the registers within the chip. I've used that technique also before and also explained it in detail in one video, card here, link in the description. And then we have a read access output at one of those read commands that of course reads those first 7 bytes of the registers that include the magnetic measurement data. And then I have get commands, also the usual structure, getting data from the object's register array, and I have here raw access output XX bits. You remember you can get 16 or 18-bit outputs from that chip, but it's not different modes. It's really just, yeah, reading 16-bit or adding 2 more least significant bits to the data. So accordingly, I have here that raw access data output 18 bits, which gets the access as a numeric value 0, 1, 2. We saw that in the sketch. And yeah, to contain these 18 bits of data, I need an unsigned integer 32, but if I only want 16 bits of data, I don't know why, but I implemented it. You also have a raw access output 16 bits, and that of course fits into an unsigned 16-bit integer. Anyway, we have that last error method that returns the last error, and then we come to the private part. And that starts with the I2C address of our device, which is fixed 0110000, and then come all our register addresses. And I haven't written down here or expressed every of the addresses as constant because it's not really necessary. Our magnetic output registers, we saw that, start as hexadecimal 00. Our temperature output register is at address hexadecimal 00. Our status register, which is also kind of a control register, hexadecimal 8, then control 0, 1, 2, and 3 at hexadecimal 9, A, B, and C. And I totally skipped that OX2F ID register. It's useless, yeah. So then I have a first register bit here defined, and that's in the control 0 register, the take measurement magnetic bit. Yeah, that was the bit 0 in the control 0 register. We will need that later in the implementation of the method. Then I have some private variables, yeah, my reference to the 2-wire. I have here my registers array, which goes to my highest register, control 3 register, plus 1, of course. And here I have a variable where I store the last encountered error in. And then I have some private methods here. They are all Boolean, so they can all fail and write something to that last error variable, which you can retrieve with the last error method. And that's first read registers that will read the first register and some consecutive registers into our array here from the chip. Then I have a write register which writes a hard value. That's something new. I think I didn't use that in the QMC library. Writes a certain value into a certain register of the chip. Then we have write register with just the register address, and that actually writes a certain value from our register array to the chip. And we have write registers, the same, but I can write several registers for my shadow registers here within the object to the chip. Here's the CPP file. So we include our .h file, and then we have here our constructor that gets that 2-wire reference as argument, and I initialize my private wire variable to that argument, and I also initialize my registers array, the shadow copies of the registers, to 0. I can do that, that's absolutely valid, because all registers in the chip are also initialized after reset or power up to 0, at least according to the datasheet. Our destructor, as mentioned, does absolutely nothing. And then we have here a bool, that's our action, take magnetic measurement. And that will write to a register of the chip, the control 0 register, of course, the content of our shadowed control 0 register in the array, binary ORed with the control 0 TMM bit, so take measurement magnetic. I don't write that bit here directly into the control register itself, into the shadow copy, and then write the shadow copy over to our chip, because that bit will be resetted automatically by the chip back to 0 after the measurement is done. Also, I have other bits here in that control 0 register. Remember, that bit we write 1 to it, then a measurement is taken and the chip will automatically reset it to 0 after the measurement is taken. We don't want to write that into the shadow array in our library itself, because yeah, it goes back to 0 anyway, so that would just cause us to do more work. In general, we want to keep all the reserved and these write-only bits 0 in our shadow copy. But at the same time, if we write the register, we want these configuration read-write bits, in this case enable automatic set reset. We will talk about that in the next video, and enable measurement done interrupt, yeah, self-explaining. We want the same values we already have in the chip to be written into the chip. Then we have the read access output, which just reads registers from the chip into our shadow array, starting with the magnetic output registers, and yeah, 7 of them. So 3 times 2 for the 16-bit values, and then the 7th one, which contains the additional 2 least significant bits for all the 3 axes. And then we have our raw access output 16-bit method, which gets as an argument the axis 0, 1, 2, so X, Y, Z. And I'm here just taking here out of my registers the magnetic output register with an offset of 2 times the axis. So offsets would be here obviously for 0, the x-axis 0, for y it would be 2, and for z it would be 4. And that's my most significant byte, so I have to turn that into a 16-bit integer and unsigned integer, and then shift it 8 to the right. And that I'm binary ORing with the least significant byte in my array, and that's exactly the same, but I add a 1 to the offset in the array. So these would be for X, Y, Z the bytes 1, 3, and 5. The raw access output 18-bit function first gets a raw access output 16-bit, so the most significant 16 bits. It casts the whole thing into an unsigned integer 32-bit and shifts it 2 bits to the left. Remember, that value is perfectly okay, it's just missing the last 2 least significant bits. And these I extract here out of the registers, magnetic output registers +6, so the 7th register. To understand the bit banging that will now happen in the code, we have another look at how that register is structured. So we have here in bit 7, 6 the least significant bits for X, in 5, 4 for Y, and in 3, 2 for Z. So, for example, if I want the least significant bits for the x-axis to be really in the least significant bit position, so at 1, 0, I have to right shift the whole thing 6 bits here and then mask out the rest. For Y, I have to shift it to the right 4 bits and then mask out the rest. And for Z, I have to shift it right 2 bits and then mask out the rest. And that's exactly what I'm doing here. So I take the content of my 7th magnetic output register and I shift it to the right by 2 times 3 minus the axis 0 to 2 I'm passing here. So 3 minus 0, that would be the x-axis, that is 3 times 2, 6 bits. Going over to the right. And then I mask out here with binary AND all the other 6 bits here, just as a matter of course. And of course, 3 minus 1 for the y-axis is 2, times 2 is 4, only 4 bits shifted. And for the z-axis, 2, 3 minus 2 is 1, only 2 bits shifted to the right. And at the end, I convert the whole thing also to an unsigned integer 32-bit and binary OR it to my already existing 16-bit value. We're done. Finally, we have that public last error method, which just returns the last error. Finally, we have all the private functions for reading and writing registers. The first being read registers, which will read registers from the chip and store them in our registers array. You remember it gets as arguments the address of the first register, which is incidentally also the offset of the first register we want to read in our registers array, and the number of registers we want to read. Again, a reference to that other video, we do a begin transmission with the device address, and then we write the address of the first register we want to read to the output buffer of the Arduino I2C library, and then we do a via AND transmission and we don't release the bus. That's the false argument here. And if something should go wrong, we store the error we got here back from that AND transmission in our last error, and we return false. And then we request a certain number of bytes, and that's our register count from the device via I2C. Of course, we have to supply our device address. And at the end, we will release the bus. That's the true argument here. And if we don't get back exactly the number of bytes we wanted, then again, error handling. And just to be on the safe side, we afterwards check via available if we have really the number of bytes available we want inside the buffer. Otherwise, error handling. And finally, we read the bytes from the I2C buffer of the VIA library into our register array, with the right offset here. And of course, we provide the number of bytes we want to write to. And if we can't read the number of bytes we want, again, we throw an error. Otherwise, everything is fine. The next private method is write registers. We already used that, and it gets the register address of the register we want to write and the value we want to write to that register. So that is not actually referencing our registers array. That comes next. So again, already explained, via begin transmission with the device address, and then we write the address of the register we want to write the value to, and then we write finally the value to our I2C output queue. And then again, we do a via end transmission with the argument of true. That is, we are finished. After that is transmitted, we will be releasing the bus. And if that somehow goes wrong, we do some error handling. Otherwise, we're okay. The last two methods are really trivial. Write register gets only the register address, and that uses the other write register method to write to the chip the specific register, but this time actually the content of our of that register in our registers array. And write registers, plural, is the same, but we get the address of the first register and then the number of registers. And then we just go through a loop and repeat a write register for every register we want to write. And that's all of the code up to now. And that's how our output looks on the serial monitor. And please note, the first time we read, remember in the loop we first read and then we issue a take magnetic measurement command to the chip. The first values we read are 0, 0, 0. Everything is initialized with zeros inside the chip at the beginning, and the chip doesn't take a magnetic measurement unless you actually, it's really working, I can scroll that, unless you tell it to take a magnetic measurement. And that's how the whole thing looks at the serial monitor. Please note again, like in the basics video, how low the noise level is on these signals. It's really astounding. And of course, if I rotate my digital compass, it's not yet a digital compass, but it will be, I get that sine dance of the blue x-axis and the red y-axis, while the z-axis in green is almost, unchanged, because the z-axis of course goes here up and down, and to change that I would have to tilt the chip, which I'm doing right now, and then I can also have different values for the z-axis. Wonderful. That's it for today. We did the groundwork for our own library, and in the next 1 or 2 videos we will explore all the functionality that chip has to offer. There will be, because of the sparseness of the datasheet, some experimentation, including even an oscilloscope. Till then, bye.